All right, welcome to class. Today is, let me make sure I'm on the right spot here. We're on lecture 14, which is systems of nonlinear equations. Okay, and if you haven't already, please stop and have an opening prayer. And I've given the TAs a quiz, so please do the opening prayer and quiz, and then resume the video. Alright, great. So, should have done the prayer, the quiz. Now we'll go ahead and start. So today we're going to do two things. The first thing we're going to do is we're going to talk about methods for systems of nonlinear equations. So methods for systems of nonlinear equations. Okay, and let me just double check my notes, make sure I'm right. That's right. And then, so we're going to talk about Picard's method again. And we're going to talk about Newton's method again. Okay, and then in 2, we're going to do an example. So an example, two-component system. Okay, so that's what we're up to today. So let's start. So first, methods for systems of nonlinear equations. Alright, so solving a multivariable system of nonlinear equations is really quite similar to solving a single nonlinear equation. We're still going to use these fixed point methods, the Picard's method and Newton's method, but we're going to have to adapt that for multiple equations now and multiple unknowns. So I'm going to write a few general equations. If they don't make sense at the beginning, don't get too hung up on them, and we'll do an example, and then hopefully the general equations will make more sense. But if I don't lay out the general equations first, it's hard to do the example. So let me lay it out first. So here's the problem. Okay, so we have the problem, and we have multiple equations and multiple unknowns. So now I have f0, so f is some function x0, x1, ... xn minus 1 equals 0. So I have multiple x's, and I'm going to have an f1 all the way down to an fn minus 1, where this is now x0, x1, ... xn minus 1, and fn minus 1 down here is the same thing, x0, x1, xn minus 1 equals 0. Okay? So notice that this is in standard form or residual form. Okay, so it equals 0. And it's convenient to rewrite this in vector form. So in vector form, this looks like the following. We have f with my underbar for vector f, x there for vector x equals 0. So in this case, f is f0, f1 to fn minus 1. And x is also this vector x0, x1, all the way to xn minus 1. Okay? And 0 also. 0 is this vector of zeros. 0, 0, down to 0. Okay? So this is just a more compact version of this guy up here. Okay? So, how are we going to solve these? We're going to use the same methods that we used in class last time when we talked about a single equation. We're going to use fixed point methods. Alright, so let me just adjust my notes here real quick so I can see them. Okay. So remember, fixed point method was x of k plus 1 equals g of x of k. Right? The difference being now that x is a vector, so this has all of the x's, x0, x1, all the way to n minus 1, and this g is a vector function of this vector. And remember, we start out with a guess, and then we get an answer, and we put it back in, and go around and around and around. Okay? So let's talk about these different ones. A, Picard's method. Alright, so in Picard's method, remember, these different methods, all they are, we're picking G. So different methods, oops, I hit the erase button there. Different methods are different G. Right, so in Picard's method, we said that G is equal to x plus f of x. Okay, so it's the same thing, except now these are all vectors. So we go through, now we have x at k plus 1. If I just plug it in, I get that x at k plus 1 is x at k plus f of x at k. And again, so if this seems a little abstract, I'm not going to write this all out, but I'll do an example of a two-component system, so two equations, two unknowns, and this should make more sense, so if you're confused by this, just hold on just a second and we'll get there, okay? But just let me remark that in Picard's method, even worse, it's even worse than in the single component, or in the single equation case. In the single equation case, we can get Picard's method to work, sometimes. In more than one equation, it gets harder and harder, and so we'll really rely on Newton's method as our workhorse for multiple equations. But we'll do an example with one that works out, just to see. Okay, Newton's method is our other one. Newton's method here. Okay, so I just remind us for a single equation, g of x was equal to x minus f of x divided by f prime of x, where that was the derivative with respect to x. So analogously, alright, with the vector g of x, this equals x vector minus, okay, here comes the part that's going to confuse everybody. It's this matrix J inverse dotted with f of x. Alright, so J, what's J? J is so this is the inverse of J. So this is the inverse of the matrix, okay, of all of the derivatives, all of the partial derivatives of f. Okay, so I'm going to write, okay, and J is called, that object is called a Jacobian. Alright, so let me write out the matrix down here. So J matrix, okay, it's equal to df, hit the erase button again. The suspense is killing us here. Let's see, where am I? df0 dx0. So remember, this f vector, okay, is this guy, right? f0, f1, f all the way down to fn minus 1. So I'm going to take df0 dx0, and then the next part of the matrix is df0 dx1, all the way to df0 dxn minus 1. So I took the derivative of the first equation with respect to each component, all the way across. The next row is df1 dx0, df1 dx1, all the way to df1 dxn minus 1. And then this continues for all the equations down to, let me scroll down a little bit so I don't hurt my wrist, writing down on the pad there, n minus 1 dx0 df n minus 1 dx1 all the way to df minus 1 dx n minus 1. Looks like I didn't make my matrix go down far enough. Okay, so one way to write this is dfi dxj, where I is the rows and j changes over the columns. Okay, so let me say a couple of things about this. So let's go back and look up here at this equation. So j is this matrix of all the derivatives, and it's the inverse that I want, okay, because this f prime is in the denominator, so the inverse, that's what makes this analogy here, times, okay, dot product with f of x. So the multi-component Newton's method is a little more complicated because we have to take all of the derivatives. So let me say a couple things about this. What else do I need to say? So first, I'm not going to do the derivation for you, but the derivation is in the notes, which is online. You're welcome to look. The derivation follows the exact same steps as the single component, or the single variable and single equation. You know, it uses a Taylor series and all this, but it does it with matrices and stuff. Okay, multiple components. The second thing I would say is I would guess that there are perhaps a couple of you who are either new to partial derivatives or have yet to see a partial derivative. And so I also have supplemental notes on partial derivatives. But if this is brand new to you, I hope not. I hope most of you have seen partial derivatives in your math class. But a partial derivative is just a derivative. It's the same derivative as you know from basic calculus, except you're holding all the other variables constant. So, here's a quick, partial derivative example. Okay. Again, go look at the supplemental notes for more. But if I have, the partial derivative with respect to x of x squared plus y squared, I treat y squared as a constant, and I just do this derivative, so I would get 2x. Okay? If I did the partial derivative of that same guy with respect to y, x squared plus y squared, I would now treat the x as constant, okay, and this guy would end up being 2y. Alright? So you can go check that out. If you have more questions about that, please let me know, because this is a new subject that I'm covering this year, and so if there are people who don't know what partial derivatives are, I'd like to know so that I can adjust this lecture accordingly and my expectations. Okay? But I'm hoping most of you know what that is. Okay. So now I've got my G. Sorry for the scrolling. I've got G here, and oh, I didn't mean to make that mark. So now I need to plug in to my equation for a fixed point method. So for the fixed point method, I can now put x at k plus 1 is equal to x at k minus j inverse of x of k dotted with f of x of k. Okay? And that came from x of k is equal to g. X of k plus 1 is g of x of k. Let me put the right vector notation under here. Alright, so this is not the most useful form for this, so I'm going to do a little bit of algebra. So I'm going to move this guy over here, okay, and I'm going to just pull the negative sign inside of this dot. So I'm going to get x of k plus 1 minus x of k equals j inverse x of k dotted with a minus f of x k. Alright, I know this is a little bit of algebra. We're almost done. We have just 2 more lines and then we go to our example. Okay, so this guy I'm going to call right here, I'm going to call, oh, not the whole, both of them together. Call this guy here delta. Okay, because it's xk plus 1 minus xk. Alright, and look at this. I'm going to then multiply both sides by j. Okay, I'm going to put a j there. I'm going to put a j there. Okay? So what do I get? I get j dot delta equals, and then that times that, a j times j inverse goes away. I get minus f of xk. Okay? So this looks like ax equals b. Ta-da! Okay? We know how to solve x equals b. This is just a linear system. This is a linear system with the matrix of the derivatives. This is my new x. This I know because I have f of x of k. So then where do I going to get xk plus 1? I'm going to have xk plus 1 equals x of k plus delta. That I got from the definition of delta right there. So these are the two equations that I need. So this guy depends on x of k here, and I use it to solve for delta, and then I just get x of k plus 1 from delta. Okay? So the steps I'm going to use here when I'm solving Newton's method, which we'll just show in just 2 seconds in our example. So I'm going to evaluate f, then I'm going to evaluate j. So these use, both of them use x of k. Okay? Once I have those two things, that's going to give me delta, or excuse me, that's my third one here, I'm going to put instead. But solve linear system. Oop, what was I writing there? Sytens, not system. Linear system. Okay, that's going to give me delta. So, on that's just, I'm going to write one more line. Okay, and then I'm going to use that to update x to x of k plus 1. Alright? Okay, so enough for the sort of just talking about that stuff. Let's do an example, and I'll show you some code. So we'll do the sort of example-y part out, and I'll show you the code. So number 2, this is our example. 2 equations, 2 unknowns. All right. Example. Okay. So here's the example. We're going to do Picard's method and Newton's method for z equals e to the minus y. That's our first equation, equation 1. And y equals 3z minus z squared. That'll be our equation 2. I'm just going to not label them equation 1 and 2. I think that'll actually be more confusing. Okay, so what am I going to do? First step here is convert to standard form. Alright? I want you to be thinking about, before I write it, what is it going to be? What's standard form? What do I have to do to get it in standard form? Alright? I'm going to move everything over, right? So I'm going to write e to the minus y minus z equals 0. And I'm going to have, let's see, y minus 3z plus z squared equals 0. Okay, so I moved everything to equal 0, but I want to go back and look up at the standard form up here for a second. I'll scroll back down, don't worry. Standard form was, I had f0, x0, f1, f0, x0, x1, etc. So my variables are named x0, x1 because I put them into this vector down here. So let me erase that one here before I forget. Okay, let me go back down. I want to rename my variables so that I can fit in that format. Alright, so I am going to make x0 equal to y and x1 equal to z. So now I rewrite that. I'm going to have e to the minus x0 minus x1 equals 0. And then I'm going to have x0 minus 3x1 plus x1 squared equals 0. Now that looks like f0 of x0, x1 equals 0, and f1 of x0, x1 equals 0. Okay? That's f of x with vector notation equals 0 in vector notation. Okay? Where f are these two guys, right? And then the x are these two guys and zeros right there. Alright, so that's my equation. So now, number 2 is write in the form of x equals g of x. So let's do that. So we have Picard's method. That one's the easier one to do. So in Picard's method, I have x, k plus 1. That one's a little funky there, isn't it? K plus 1 equals x of k plus f of x of k. Okay, so now what do I need to do? Let me plug that in. So x is x0, x1, k plus 1, k plus 1 equals, and what's over on this side? I have x0 at k, x1 at k, plus, and now I just have, oh man, I didn't do that very good, did I? F, so what's f? F is right up here. F0 is just right, that guy right there. I tried to point as if you could see, but you can't see. I have to show it up here. It's this one right here, right? That's F0. So let me put that down there. Oh, I don't know if I'm going to be able to do that with my wrist. Down here, handwriting. F0 is e to the minus x0 minus x1. Great. Okay, and these x's are going to be at k, because this is x of k. And then f1 is x0 at k minus 3x1 at scribbly k plus, sorry for my k's, x1 at k squared. Okay, well now I can, oh, need to add a new page. New page after. And then for some reason I always jumps to the bottom of the page. Okay, so now I can rewrite, this is now two equations. x0, k plus 1 is equal to x0 at k, forgetting some of my parentheses on these, not equals, I already have an equals, plus e to the minus x0 at k minus x1 at k. And then x1 at k plus 1 is equal to x1 at k plus x0 at k minus 3x1 at k plus x1 at k, and then the whole thing squared. Okay, and notice this x1 and that's going to combine and give me minus 2. Okay, but you know, I could type that out or I can cancel that. There you go. There's Picard's method. That's the easy version. Okay, Newton's method. Okay, so in Newton's method, remember I have J dot delta equals minus F. So what do I need to do? Oh, and then I have x at k plus 1 equals x at k plus delta. Don't forget the minus. Okay, some of you are going to forget the minus. So the hardest part about Newton's method, I guess there's kind of two hard parts. Remember what I said before, the hard part about is getting f, is setting it up in the standard form, right? So this one's a little harder because when you set it up in standard form, you got to pick x0, x1, etc. Okay? This choice here, x0 and x1, this is arbitrary. It didn't matter. I could pick either way. Okay? If I'd have picked x0 to be z and x1 to be y, it wouldn't matter. Okay? And if I'd have picked this one to be, this guy right here, if I'd have picked that to be equation 1 and this to be equation 0, it didn't matter. Okay? That doesn't change what happens in the method. Alright? So what do I have to do? So that's the first hardest part, is picking the f and remembering the minus sign. The second hardest part is getting the derivatives. Okay? So j, I said, was the derivatives of all these guys. So this is going to be df0 dx0, and this is df0 dx1. Down here I have df1 dx0 and df1 dx1. So I need to take all those derivatives. So what are they, right? What is df0 dx0? Well, I just plug in up here the f, right? f0. That was this guy right here. f0 and f1 is that guy. So let me come down here and do those derivatives. So df0 dx0 is dx0 of, okay, now I need to plug in. It was e to the minus x0 minus x1. Okay, well, what I say what a partial derivative is? I take the derivative of this guy with respect to x0, which is minus e to the minus x0, and that with respect to x0 is just 0. That was it. That was pretty easy derivative. df0 dx1 is my next one. So I have the derivative with respect to x1 of e to the minus x0 minus x1. Well, that's 0. Doesn't depend on x1. And that becomes minus 1. Yes, I like easy derivatives. Okay, perfect. Keep going. So now I have df1 dx0. Okay, this is going to be the derivative with respect to x0 of the second equation. And the second equation is something like the following. Good thing I have it on my notes because we lost it up at the top. x0 minus 3x1 plus x1 squared. Let's check up here, make sure we're right. x0 minus 3x1. There you go, right there. I keep trying to point at it as if you're here. Plus x1 squared. Sorry for pointing at the camera. Okay, so take that with respect to x0. Well, that one's going to be 1, and that's 0, and that's 0. So that's 1. The last one is df1 dx1 equals derivative with respect to x1 of x0 minus 3x1 plus x1 squared, and that's going to be 0. The derivative of minus 3x1 is minus 3. The derivative of x1 squared is positive 2x1. Alright, so now I need to just plug into my formula. So I have j, which I'm going to plug in. Remember, I had that matrix of those guys, so this will be e to the minus x0, and this one minus 1, 1, and 2x1 minus 3. Dotted with delta 0, delta 1 equals, and then on the right side I have a minus, and I put in my equation, right? Minus x1 of k plus e to the minus x0 of k. And then over here I had x0, well, that was kind of terrible. Let me scroll down a little bit. I'll fix that one. That x0 gets fixed. That's going to be x0 of k minus 3x1 plus x1 squared. Oh, I forgot to put my k's in here. K there, And I'm going to have to fix that k there and make that guy squared. Okay, and I forgot to say over here, this x0 has a k on it, and this x1 has a k. Right? So how are you going to solve that, right? So you're going to have an x of k, you're going to guess. That's going to give you a matrix. You put in the x1 of k, x0 of k on both the left-hand side and the right-hand side, and you're going to solve and get out d0, d1. And then you're going to get x0 of k plus 1 is going to equal delta 0 plus x0 at k. And x1 at k plus 1 is equal to delta 1 plus x1 at k. Okay? So that's an example of going through Newton's method. So I will show you the code. Now might be a good time to pause if you need a second to ask the TAs a couple questions about what I did. These notes will be posted online, hopefully already, and hopefully you'll be able to see them. Alright, so you can pause if you need for a second. Okay, so now let us look at the code. So let me move my face down so you can see it down here. Oh, big Dr. Tree. Move this over up to this corner maybe. Okay, so I'm just going to show you, oh, I better make this a little smaller. So let me quick zoom in here. So let's make this maybe like 18 so you can see my screen a little better. Alright, so I took these two equations and I just made a plot. So I want to show you the plot real quick. So here's the plot of what they look like. Okay, so one is e to the minus x and it's going like this. And the other is a quadratic, but it's on its side. So they cross at two different points, which are these green points, which are the solutions right there, which I found by Newton's method, Picard's method. So here is an equation for Picard's method. So I import numpy as np, and I define a function, and that function has, notice this is a vector function, and x is a vector coming in. So x is this array, which has two parts, 0 and 1. So I define two new variables, x0 and x1, and I write my two functions, f0, which is the exponent of minus x0 minus x1, and f1, which is my second equation, x0 plus etc. Alright, and the return returns an array of f0 and f1. Right? This is super important. This is the part people are going to miss. Okay, don't put x0 comma x1 up here. This needs to be in a vector. That's the standard form. Alright, and f needs to return a vector. So don't put return f0 comma f1, put it in an array. So it needs to have an array that comes in and an array that goes out. Right? That's probably the hardest part about coding this. So now I have my tolerance and Kmax, which are the things, the tolerance is how accurate I'm going to solve it to. Kmax is the maximum number of iterations. I'm going to let the fixed point method go. Now I have k equals 0 is where I start out, and I start out with some guess. Alright, and I calculate the residual by evaluating f at x. So notice that my guess is an array. Alright, and my residual, I need to take the norm of that array. So I take the norm of f, which returns an array, and that's going to give me some value for the residual. Here's some print statements just to print out at every step what k is, what x0, what x1, and what the residual is in my method. Alright, now for Picard's method. So here's another print statement, and I say while the residual is greater than the tolerance, I do x is assigned to x plus f of x. That was what I said Picard's method is. So I don't even have to write it all out like I did by hand before. I just plug it in because I have it up in my function up here. Then I increment k, and I calculate my residual, and off I go again. Alright, so let's run it. Let's see what happens. So I guessed 0, 0. So I'm guessing down here on this guy. So I'm guessing that my solution will find this one over here, which is near 1 and like 1/2. on the x0, x1 plane. So let me come up, press go on this, and that made that guy pretty big. Maybe I can zoom out. There. Alright, so I started out at 0, 0. My residual was kind of big, kind of bounced around a little bit, and eventually it caught on and it converged. And I did indeed get the 0.98 and the 0.37. So, which was this point on my plot right there. Okay, now let's look at Newton's method. So in Newton's method, I import NumPy as NP, and I define my function again. Same thing here on this function. I have f is a vector function of x, a vector input. And I take x in, and I take the components of x, and I assign them to new variables. I don't need to take them out as components. I could substitute here x, I can make this x at 0 everywhere. Okay, that's fine. Or if I wanted to write the original equations, where this one was y, okay, and this was z, I could do that, and then type these guys in here as y and z, if I wanted. Okay, but I'm doing it this way. Then I define my functions, and I return the array f0 and f1. Okay, now the Jacobian is a matrix function. It takes in a vector x, and it returns a matrix. So I have x0 and x1 here, and then each one of these equations are each one of the derivatives I took. So that was the Jacobian derivatives, minus e to the x0, minus 1, 1, 2x minus 3. Okay, and then I return a matrix of each of those 4 equations. So notice this is 2 lines here, right? This is the top row of the matrix, this is the bottom row of the matrix, and I have to have the double bracket around the matrix. And I return the matrix. So now I've returned the Jacobian. So from there, okay, it's very similar to Picard's method. I have a tolerance and a Kmax, which are the same. I start out with 0 on my iteration, okay, and I make my guess, which again I guess is 0, 0. And I calculate the residual by taking the norm by evaluating the function which is in standard form, which is in residual form. Okay, couple print statements, and I get to my while loop, and I say, well, my residual is greater than the tolerance, I'm going to keep going. And notice now what I do, okay? This is the difference between Picard's method and Newton's method, right here, on lines 38 and 39. So on line 38, I say delta is going to be numpy.linalg.solve j of x. So j of x, that's going to evaluate my Jacobian at the old x. And then that's my a, right? ax equals b. My b, the right-hand side, is minus f of x, which is a value right there, and it gives me delta. And then I increment x by adding onto it x, plus delta, right? Adding delta onto it. So x is assigned x plus delta. So those are 2 lines. Note that, you don't have to go back and code Gauss elimination or other things, right? We learned the easy way of solving it, so now we can use that in just 1 line. Call the linear algebra solver on the ax equals b. Once I do that, I increment k, calculate my residual again, and let it go. Okay, let's run Newton's method and see what happens. Boom. Newton's method. Look how fast it converged. It only took me 5 steps, which is great. Newton's method's awesome. But the last one, it can't even detect an error. It gets so close. Okay? And there again, I calculate the same thing. Notice that if I change my guess on Newton's method to one that's minus 1, 3, which is close by that other point, I can run this one again, and out I get the other root. Now I have minus 1.2 and 3.36, and that's what I get. Alright, that is all I have for you today. If you have questions, please ask the TAs. If you have any time left, I'm not sure if I got the exact time here. If you have any time left, you can go ahead and look at your homework and ask the TAs for help on that. Alright, we'll see you next time.